I've shown you how to multiply two matrices together or add them together, and now we're going to look at why it should be that way and what are the usefulness or the applications of matrices. So this whole area of maths that involves matrices is generally called linear algebra. So I'm going to talk about the linear part of that first. So the term linear is generally applied to functions. So let's say I have a function f of x. We say that function is linear if f of x plus y is always equal to f of x plus f of y, and also that f of ax is always equal to a times f of x. If I plot a function that has these two properties, it will always look like this, a straight line through the origin. Let's put some numbers in here and see how those properties work. Let's say here is 1 and 2. So here is f of 1 and here is f of 2. Now, for a linear function, from that first property, I should have that f of 1 plus 2 is equal to f of 1 plus f of 2. And for a straight line like this, that will actually be the case. Because for a straight line, if I go over in the x direction, along here, no matter where I am, I will always go up the same amount in the y direction. So if I go over 1 here, I go up a certain amount here. And if I go over 2, I go up twice that amount. And so even if I do my f of 1 first, right, I go 1 here and I go to f of 1. So there's my f of 1. And then when I go over another 2, so f of 1 plus 2, I'm going to start here and I'm going to go over another 2. So let's say I'm going to start from here and go over 1, 2 to here. So I'm going to be up here now. But actually, my increase from here up to here is the same as the increase from here up to here, because it doesn't matter where I am on a straight line. If I go over 2, I'll go up a certain amount. And so if I go directly to f of 1 plus 2 is 3 over here, and get f of that, I get the same answer as if I had just got f of 1, got f of 2, and added them together. Right? And this will be true of straight lines and not true of any other kind of curve. It also won't work if my line doesn't go through the origin. So the other property there is that f of ax is equal to a times f of x. Well, that just means that, I go a certain amount up for every 1 I go over. And if I want to go over a times that, let's say I go over 3 times 1, I go up 3 times f of 1. So again, this is another property of straight lines functions. So what kind of functions can be linear like that? Well, actually, there's only one kind. And f of x has to be equal to just some number a times x. So some examples could be like f of x is equal to 2x, or f of x is equal to 5x, or f of x is equal to minus 10 times x. Those would all be functions that satisfy these properties and are linear functions of one variable. So now we can extend this notion to more than one variable. So let's say I have a function of x, y, and z, a function of 3 variables. So you can think of this as something that takes in 3 numbers and spits out 1 number. For this to be linear, it will have to be of this form: a times x plus b times y plus c times z. So a function like this will satisfy our properties to be linear. So you can see that if, for example, I multiply all my input by 2, I get with 2a times x, 2by, 2cz, and if I factorize, I find I just have twice the output. So it satisfies this function that, f of a times x should be equal to a times f of x. Now, what about the other property, where I should be able to add together 2 inputs, and the output should be the same as if I did them separately and added the outputs? So what does it mean to add together 2 inputs here? Well, at this point, I'm going to make the connection to matrices. And I'm just going to write down my input here like this. And I'm going to call it X, capital X. So that big X now is a 3 by 1 matrix. Another way that you might write this is like this, X bar or X arrow, and call it a vector instead. But we haven't got onto vectors yet, so for now we'll just say it's a 3 by 1 matrix. Now our function looks like this, f of big X. And the property we want to satisfy for linearity is this, that f of 2 times x is equal to 2 times f of x, like it was for a function of one variable. And that's what we've written above here as well, up here. Now what if we wanted f of two of these added together? Let's say I have these two 3 by 1 matrices, and I want to know, well, what is f of x plus p? And is it equal to f of x plus f of p? So remember our function, f of x is equal to a times x plus b times y plus c times z. F of p is equal to a times p plus b times q plus c times r. So what's x plus p? Well, it's equal to x plus p, y plus q, z plus r. This 3 by 1 matrix, and then f of that is equal to a times x plus p plus b times y plus q plus c times z plus r. And if you go back now and look at f of x and f of p, I think you can see that when we add this to this, we will get this. So there I have, when I add them up, I'll have ax plus ap will be equal to a times x plus p, and so on. So as long as my function f is of this form, where I just take each variable, multiply it by some number, and then add them all up, then we satisfy our two properties. And so these are linear functions, and it turns out that these are the only kinds of functions which are linear. And finally, we can express these kinds of functions as a matrix multiplication. So let's say I let A equal to A, B, C, a 1 by 3 matrix. Now, f of x is just equal to ABC times XYZ. So, if I multiply out that matrix, I get A times X plus B times Y plus C times Z. But this is nothing else but A times X, a matrix multiplication. So this matrix A here represents some linear function. And that X matrix there represents this variable, which is actually 3 variables in this case, and can be as many variables as you like, just gathered up into a matrix with the right size. Let's look at some examples. Let's look at a function that gives you the sum of 3 numbers. So f of, say, x, y, and z, in this case, is just x plus y plus z. It's the sum of the 3 of them. So what's the matrix version of this? Well, the matrix that does that would be just 1, 1, 1. And our x then again is still just x, y, z, those 3 variables gathered up into a matrix. So let's multiply that out. Ax is, as expected, just x plus y plus z. So the appropriate matrix for a function that just sums your variables will be 1, 1, 1. How about a function that gets the average? In this case, f of x, y, and z will be equal to x plus y plus z over 3. Or that's the same as saying 1/3 times x plus 1/3 times y plus 1/3 times z. So the matrix for that would be 1/3, 1/3, 1/3. So there's my a for that, and if I multiply that out now, a times x does in fact equal to 1/3 x plus 1/3 y plus 1/3 z. And the point of all this is that any function of multiple variables which is linear can be expressed in the form of a matrix A, which you multiply by your matrix with your variables in it. Now, in this case, our function matrix, our A, has always been what you might call a row vector, in that it's one row, and our variables have always been in what you might call a column vector, in that it's all in one column. Next, let's look at the case where you have multiple variables coming into your function, but you also have multiple numbers coming out. So let's say I have 3 numbers, and I'm going to calculate another 3 numbers from that list of 3 numbers. So here I have my 3 numbers, x, y, and z, that I'm putting into a function, and this function will return 2 times the first number, plus 1 times the second, plus 1 times the third. Now, what if I wanted a function where I put in 3 numbers, like x, y, and z, but I actually get out 2 different numbers? How would I write something like that? Well, it turns out I can just add another row here. Let's say it's 0, 1, 2, for example. And you'll find that when you multiply this out, I'll get that first row the same. But if we do a matrix multiplication here, I'm actually going to get a 2 by 1 matrix out here. And my second element there will be the second row here times my variables. So I'm going to get 0 times x plus y plus 2z. What if I wanted a third number to come out of this? Well, I can just add another row again. So this time, let's say it's 1, 0, 0. Well, then I'm going to have a third element in my result, and it's going to be 1 times x plus 0 times y plus 0 times z. So there we have a 3 by 3 matrix that represents a function which takes in a list of 3 numbers and spits out another list of 3 numbers. And any linear function like that can be expressed as a matrix. Now, you can see from this that, say I'm taking in 3 numbers like that, x, y, and z. I can write a matrix that calculates any number of numbers from those 3 numbers. It just depends on how many rows I put in my matrix. The square matrix here is kind of a special case in that you get the same number of variables out that you put in. So here I have 3 x, y, and z. So the 3 by 3 matrix gives me 3 variables out. So we're mostly going to be looking at square matrices like this, because in this case it's the same kind of thing that you get out that you put in. It's the same amount of numbers. For example, if I look at 2 by 2, I can write a matrix like that, x, y, and I can write something here, some other matrix. So that matrix represents some function from 2 variables, x and y, onto another 2 variables. So in this case I get x plus 2y and x plus 3y. Now, matrices are useful for a lot of things, but this connection to linear functions and being able to take in a list of numbers and spit out another list of numbers according to some linear function, that's a big reason why matrices are the way they are and why the multiplying and adding works the way it does. A matrix is not just some random box of numbers, it represents a linear function. Let's say I want a function that takes in 4 numbers, x, y, z, and p, and it swaps the first 2. Can I come up with a matrix that will do that for me? Well, how about this one? It's going to be a 4 by 4 in this case. And so what's the first row of this matrix going to be? Well, I want it to act on x, y, z, and p, right? And I want it to return y in the first place. So what does the first row need to be to give me y? Well, how many x's do I need? Well, it's 0. How many y's? 1. No z's and no p's. So multiply this out now. This multiplied by this gives me my first element. So 0 times x, 1 times y, 0 z, 0 p gives me 1 times y. In the next place here, I want x. So, for my second row, I want 1 times x, so I put a 1. And I don't want anything else, so the rest are zeros. And that gives me my x. Now the next two rows aren't going to change, but let's go through them. So in this row here, I want something that when I multiply it by this, I get z. So z is in the third position there, so it's going to be 0, 0, 1, 0. And I want p in my last position, so it's going to be 0, 0, 0, 1. So again, when I multiply this out by this, I get no x, no y, no z, and 1p. P. So there's a matrix that represents a function that takes in this list of 4 numbers and swaps around the first 2. What about a function that takes in a list of numbers and returns back exactly the same list of numbers? What would be the matrix for that? Well, that matrix would be the one that you multiply by something to get back exactly the same thing. And in fact, for, let's say, a 3 by 3, it's just the identity matrix. And you can actually go through that piece by piece. You know, you multiply out each row. You'll see that each row just, when you multiply it out, gives you back the element from the same row. So you get x, y, z out again. And if you look back up here, you'll see in this one, all I've done is take an identity matrix and actually swap the first 2 rows to get a matrix which swaps the first 2 rows of some list of numbers. Now, when we talk about systems of linear equations, we're talking about having some list of numbers, we call it x, some function that acts on that list of numbers, we represent it by the matrix A, and that gives us some output, another list of numbers. Now, we'll be looking at cases where the size of A and B is the same. So, you know, if you've got a list of 5 numbers, your function will give you another list of 5 numbers from it. And what we're going to be interested in now is working in the other way. Let's say we're given B and we want to know what numbers did we put into that function to get B out. So it's like we're given the output of one of these functions and we're asked what was the input. We have 3 ways of doing that. The inverse matrix method, where we get the inverse of A, we multiply it by B to get X. There's a formula called Cramer's rule, and there's an algorithm called Gaussian elimination. And we'll go through all of those in other videos. So that's it for now.